So with this addition, I think I can do this one, this one, this one, and this one all at the same time. Okay, because there's only this bit that's changing there. So what we need to check is 1, 1, 1, 1, 1, right? Because it doesn't. We'll check this bit later. But 2, 3, 4, 5 ones, 3 zeros. Okay, F8 is what we need to end with that. So, oh, sorry, I don't need to check that one. It's 4 ones, not 5 ones. F0. All right, so this is both add and add with carry. So that's add and add with carry. Yep, so we're calling add function that we made before. Okay. And then we need the register, so that's going to be mask 8 0 opcode. Okay, that is extremely complicated, so let me just make sure I've got everything right here. Yes, it is very complicated. It's also very wrong in 2 places. I do notice it later, so don't worry. So now we've got ADI and ACI. So what do these do? 1 byte next instruction added to A. Okay, well that's simple enough. So case C6, which is ADI. Okay, and ACI. So case CE, which is ECI. Okay, then we can get on to subtract, and there's a trick with subtract. So with subtract, there's a little trick we can do. So we can basically use the same function, add, because subtract is just the inverse of addition. So let's make another wrapper for sub. Like that. Now what we can do is we can basically call, so if we say int x equals add, okay, and what we need to do is bitwise invert value, and we're going to have to bit strip that, and then we need to invert cy. So cy is either going to be 1 or 0, so we can say cy equals 0, then it's 1 or 0. Okay, so what that does is it inverts all the bits in value and inverts the carry bit, and that will then perform a subtraction instead of an addition. And then what we need to do now is just invert the carry flag that we get back. In sub it's actually called a borrow flag, but yeah, same difference. So that's basically oops, I need to return x, don't I? There we go. And that's it. That should do the subtraction. So we can pretty much just copy paste all of this and replace it with sub. Oh, and another thing, I forgot to put get reg in there. I've corrected that off camera, but yes, that's, if you notice that, I have corrected that. So yep, that's subtract done. Okay, so I've done the logical operations, and I've got down to compare, so they're all here. Now compare is basically functionally identical to subtract, except you don't store any result. So all we really need to do here is call sub, and that's it. We can use the same case here. This is CMP, And that should be it for compare. And this time with sub, we're not storing the result, because all compare does is set the flags. It doesn't actually store the result. Okay, so we're getting close now. I've just done a bunch of conditional jumps and stack pushes and pops and what have you. And now we've got to the input and output instructions for ports. So that's something we've got to implement. So we'll come up here. Okay, we'll do it at the top. So these are going to be abstract methods. They're going to be handled by the subclass. Okay, so that's the prototypes for that. So case D8, and that is in. Okay, and port out. So case D3, which is out. So there we go. Input output sorted. Okay, so we've now implemented all the opcodes. Bloody load of them. And what I've done is I've also moved the ranged cases to the bottom of the switch block. That way all the single cases will get evaluated first. That's just in case any of these ranges overlap any of the single instructions. So I've noticed a few errors and fixed them. I may have mentioned that in post-production. But there are a couple of things I need to add. So here we have bools for stuff, and I need to add another bool, which is IREC for interrupt request. Now, that basically just tells the emulator if there's an interrupt pending. We also need to set a method so that another class can call an interrupt. So interrupt request. I'm going to put everything above execute because execute is huge. So we'll make a reset. So we'll make this public as well. So public void reset. Okay, now we need to do a step instruction. I'm not sure to make this public or private, to be honest. No, we'll make it public. Okay, and step. In fact, what I'm going to do with reset is I'm going to pass in a variable, which is what's going to be set for the program counter. Okay, for step, so we need to basically execute the next byte. Okay, seems logical enough. But first we really should check, so if interrupts are enabled and there's an interrupt request, we disable interrupts, we clear the interrupt request, and we come out of a halted state if we are halted, and then we execute the opcode that was sent to us, which will be the interrupt vector. Otherwise, else, if we're not halted, then we can execute the next byte. Otherwise, we're going to add 4 to the clock counter. Okay, you'll see why we need to do that later. So now we want to make it actually run. So public void start. Okay, so this is going to continually run it rather than just stepping through instructions. So I'll do a while true for now. In fact, what we'll do is we'll set a boolean called running, and we'll give that a default value of false. So if we start, we can say while running, we set running to true here, and then public void stop. This will be running equals false. So while we're running, we're basically just calling a step, but we need some kind of timing thing because that's just going to race the CPU to hell. So what we can do is use a stopwatch. So let's create a stopwatch. Okay, and we'll start the stopwatch. So what the stopwatch does is it ticks. It's usually around about 100 nanoseconds per tick, but it depends on the system. But there is something called, it's a static stopwatch dot frequency, which tells us how many ticks the stopwatch will tick every second. So the Altair 8800 ran about 2 megahertz, so we're just going to set it at that for now. We can muck about with the speed later. But basically what that means, 2 megahertz means every clock cycle is about 500 nanoseconds. So if we set a long nanos per tick, and that's going to be equal to, so how many nanoseconds are there in a second? Well, there's 1,000 milliseconds, there's 1,000,000 microseconds, and there's 1,000 million nanoseconds. So we want 1,000 million, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, that's a long, and we want to divide that by stopwatch dot frequency, and what that will give us is the amount of nanoseconds every time the watch ticks. So if we now take watch ticks, multiply it by nanos per tick, that gives us the amount of elapsed time, real time. So we'll call that real nanos, and that's going to be equal to watch dot elapsed ticks multiplied by nanos per tick. Okay, and we'll have emu nanos, which is emulated nanoseconds. This is the amount of nanoseconds that should have actually elapsed if we were running on original hardware, and that's going to be CLK for clock cycles, and that's multiplied by, and remember it's 500 nanoseconds per cycle, so we multiply that by 500. So what we have now is the amount of nanoseconds which have actually passed and the amount of nanoseconds that should have passed. Emu nanos, okay, and we take away real nanos, because the real nanoseconds should always be smaller because the emulator is going to be faster, right? So if that gets behind by about, let's say 10 milliseconds, so 1/100th of a second, so a millisecond is 1,000 nanoseconds, so that's 10,000 nanos. So, and we'll thread dot sleep for 10 milliseconds. So thread sleep isn't particularly accurate. Windows isn't a real-time operating system, so that's not really going to sleep for 10 milliseconds. It might be a bit less, it might be a bit more, but it doesn't matter. It's short enough that it shouldn't be noticeable, and any errors will will compensate for themselves as it continues. So just as long as we've got some form of sleep going on somewhere, doesn't really matter how long it is, to be honest, then it should keep everything in time. Okay, I'm 3 orders of magnitude out of there. There's 1 million nanoseconds in a millisecond. Okay, right. Okay, so that should keep our timing in. And we're also going to put, so I'm actually going to make that private. Okay, and we'll make a public void run. And we'll start a task, run, start. And just here, we'll only do that if we're not running. I don't know if I should save the task object or not. Well, I think past me there is ready for a break. I do sound a bit tired, to be honest. Task is a disposable object, so yeah, I do have to save it. Fortunately, I do realise that later on. I think that's everything we need for the processor. There's almost certainly 100 errors here, but you know, we'll come across those when we come across them, I guess. Alright, so a few tweaks here. I've renamed the interrupt variables because they were a bit obscure. I've also added something called int hold. Now the reason for that is when an interrupt is called, it disables the interrupt flag, and the reason for that is so that you don't get an interrupt called during an interrupt. You know, that's not bad for you, that's not good for your stack memory. But the thing is, an interrupt will have to re-enable interrupts before it finishes. Now it usually does that right before the return for that routine. Now of course, if you've got an interrupt pending, okay, so if another interrupt has been fired during that routine, the second it enables the interrupts again, the next interrupt will fire before the old routine has had a chance to exit. So you have to just make it hold for one instruction before you actually allow another interrupt to fire. So that's what int hold does. I've also now saved the task object so that when stop is called, it will wait for the runtime system to actually shut down. And step, I've changed the way that step works so that if step is called externally, it won't step if the runtime system is active. It'll only step, you know, if it's not running. So we can get on with actually emulating the hardware now, the RAM, ports and all that stuff. Please be aware that I'm not recording everything that I do. Okay, so code may appear, things might get changed, errors might get fixed that you haven't seen me do. That's because I've done them off camera. Freestyle coding is absolutely fraught with errors and omissions. So, and it's just a question of constantly having to go back over things all the time. So just be aware. Okay, just a quick error fix that I've just noticed on add, the add function that we made. Here, where we're setting the auxiliary carry flag, I had X there. That was wrong, that should have been val. So I've corrected that, just in case you noticed that earlier. Okay, so let's create, just save all of this. Let's create the hardware class. So, and this is going to implement it's going to extend i8080, and then we'll just call we'll just make IntelliSense fill in the, there we go. Okay, so we need some RAM, so let's give ourselves some RAM. We may as well give ourselves the maximum. Okay, so read byte, that's simple enough. We just need to return RAM address. And write byte, that's RAM address equals value. It's not going to like that because it's an int that's being passed, so we'll convert it to byte. There we go. There are a few things that we need to do here, like basically the front switches of the Altair. The system can read those switches, and generally they're used to tell software what kind of hardware you're using. So you'd set certain switches to say I'm using this type of serial port or this type of disk drive or whatever. Okay, so these are the front switches. I'm storing all that data as a byte there, and then we'll have a public access method which we can set them. Okay, so we come in and we create a byte from the switch number, which we modulo with 8, and we do that so that the switches are actually numbered A8 to A15. Okay, so that just allows us to use A8 to A15, you know, when we set the switch number, rather than having to translate it into 0 to 7. Then we create sort of an inverted bit mask for that particular bit. Then we set the bit, okay, make sure that the bit is set, and if we're trying to clear it, then we XOR it to make sure that it's clear. On port in, the way the system reads those switches is by using input port FF, and it expects a response to tell it the state of those switches, so that's what we've done there. Let's make an interface, and this is, we're going to have an input device and another interface, and this is output device. So those are our two interfaces we need for that. So we also need a way to register those interfaces with this class so that it knows about them. So we'll create two dictionaries for that. So public register input device. Okay, we probably ought to check as well that we're not, nah, it doesn't matter, it's just going to overwrite it if there's one already there. We'll do this in a default case. There we go. And similarly with port out. Alright. Okay, it's been about a day and I've done a lot of work here. It turns out this reference is pretty bad. I mean, it gets the majority of stuff right, but it's there's a lot of errors in it. So I came across this, which is on the Altair clone website, which is the assembly programming reference manual, and using this I've basically dry run through pretty much everything, and I found an absolute bunch of errors that I'd made. I couldn't get this DAA right because there's so much conflicting information, but what I did find was a table which told you all the results from what you put into it when you execute it, and I created this switch block. But yeah, that is an absolute nightmare, DAA. So I've also made a monitor output which will just dump out a bunch of information about registers, memory, what's on the stack and stuff like that. that might help a great deal. And also in run, there's a bit of temporary code here. Now I've found on this website, where are we? Here, yeah. There's a bunch of test programs. Okay, but these are supposed to be run from CP/M, but that's not a huge deal because all you do is load them in at address hex 100 and then just start them running from there. And all these things do, from what I can see, is just print things to the screen. Now in CP/M, the screen print is a jump table. Well, there's a bunch of jump tables, a bunch of jumps in a table at the beginning of memory, and print to screen, well, print to printer really, but it's the same kind of thing, is at address 5. So what I've done during step is I've made a kind of breakpoint here, and if execution gets to 5, it will come out of here and then it will just display on the console window here anything that code is trying to output. So we should be able to load in a test program, execute it, and see if it spits anything out. Now, shouldn't really put it in the constructor, but this is only temporary. So, right, now we need to load in the test program. Now, I already have it downloaded. I downloaded the test8080.com, which is supposed to be the best one. And we can also look at the source code for this testing as well, which is useful, because if it fails, we can use the stack, see where it failed, and cross-reference what might be wrong. Okay, so we need to load in that test program. So right RAM, that's it. I'm not sure if I showed that last time, but yeah, I made a function so that I can write things to memory. Kind of needed. I think that's it. And then run it. And then I guess we'll see what happens. So we'll bring the debug window, the monitor window, output window to the front and see what happens. Oh, we've got some output. Okay, what we got? Oh, well, it's outputted its well, okay, that's a good sign, but it's just repeating itself. It just looks like it's starting again. Okay, not getting any kind of report of anything succeeding or failing. It just looks like it's looping. Okay, well, that's not helpful really, but it is at least outputting something, so that's one good thing. So let me see if I can find out what's wrong. I'll pause for this because it might take quite a while. Okay, so I think I know what I've done here. Well, I'm pretty sure I know what I've done. So I've updated all of this a little bit. So rather than using that console window, I can actually show things on here. It's a lot easier. I'm back referencing classes, but it's only temporary, so. And I can also step through the execution. Now, when I do this, I notice something, that when I jump to 5, which is to display some text, there's nothing there. There should be a return there. That's why it keeps looping around. Okay, because there's just a bunch of zeros at the beginning, so you've got 100 hex nops, and then the program starts again. So I think that's easy enough to fix. So we just need to put a return instruction at address 5. So write byte at address 5, and the return instruction is C9. Okay, let's see if we get anything else now. Okay, now we've got CPU has failed. Okay, well, I wasn't expecting anything else, but okay, if we look at the stack here, so if we look at the code, let's go into this test code, and the stack is 6A6. Okay, see where that is. 6A6, that's show error. Okay, so it's probably the one before that. 5A7. Okay, what are we testing here? Testing STC. STC. So it failed on STC by the look of it. Opcode 37. 37. STC. Okay, let's see what that does. STC, set carry. The carry bit is set to 1. Alright, well that's simple enough. I must have not implemented that. Okay. Right, let's implement it. Case. That's simple enough. To give it. Oh. Cannot implicitly convert. Oh. Yeah, because I'm using the int version of it. There we go. CF. Okay, let's try again. Run. CPU is operational. Wow,